Hi, good morning to everyone. So here I am again to continue with our video tutorials of MS2LDA 2.0. In this video, we are going to see how to use the MS2LDA 2.0 biz website. So this means that we can use a website in your browser to visualize the results of our MS2LDA analysis. And to do this, I will first share my screen. So we will start again from the documentation page. And here it will go now to the user guide. Then you see the different steps for processing, modeling, annotation, and visualization. And what we will focus today on is on how to visualize and explore our results. So basically, in the bottom of the page, we see that we can try the visualization website directly in the browser. And here we can load previously generated files or the demo that are incorporating the samples or the case studies of the preprint. It is important to know that you can only run the visualization, or you can only load results that are processed with the new version of MS2LDA. And let us just try it out. So if we click here, we will go to the visualization page. And right here, you see that we can load the results from our analysis. So it means that if we have already processed our data with MS2LDA 2.0, then here we will get a compressed JSON file that will have all our results. So we can drag and drop that file directly here or load it from our computer. Since I work with fungal natural products, I will load the mushroom demo. And in the moment, we will wait a bit while it loads. So just that everyone is aware of what we will be discussing today. So we will go to the preprint, which is in bioRxiv, and we will see the case study that we're going to use. So while it charges, here we see that our demo data results have been loaded successfully. So basically now it has enabled the other tabs, so the motif rankings, motif details, spectra search, view network, or motif search, which are here on. So, okay, here we have the preprint, and if we will then download the PDF, we will be able to see the different examples and the results that the authors have found and how this reflects into the master motifs that we'll see today. So let us just quickly scroll down through the paper and let's go to the results. So here we have a case study on pesticides, but down further, we can see the case study on natural products, and this is a case study that explores the metabolome of a very special fungus. And it's an edible mushroom that produces erinacerines, hericinones, and ergostans. So this was a study from that reuses the data set from the paper from Katit et al. And it brings it down to a substructure analysis. So here we have the description or the figure that deals with the erinacerines and the master motifs that are associated to them. And then we can actually try to see in the visualization website if we find those motifs. So let us do that. So since the demo is already loaded, we can go here to the motif rankings. And in this first page, we can actually be able to filter the master motifs that have been discovered based on their dog topic probability or their overlap score. In addition, we can also use MySQL queries to look through them and see which ones retrieved some hits based on the MySQL queries that are of interest. So basically, we see that in this example, like different master motifs have been encountered for these compounds. And such is the case of the erinaceric N, which has master motif 22 and master motif 137. So master motif 22 represents, according to the paper, the right side of this structure, while motif 137 represents the the left side of the structure, which includes this aromatic ring with a nitrogen. So if we would like to go through and look at motif 137, for instance, we can filter those motifs and look specifically for that one. So basically we see here for motif 137 that it appears in 85 different spectra or documents with this corresponding probability and scores. And we can see here the smiles for the spec2vec annotation. We can also export this to a JSON or a CSV file if we would like to further work with that. So right now I will click on it. And what it will do is that it will take us to the motif details page. And the first thing that we see here is the spec2vec matching results. Here we have a chemical drawing of the structural annotation based on spec2vec. And basically, we can try to use this as a guidance for our annotation of the master motifs. This doesn't mean that these annotations are 100% accurate, but it's just a starting point to go through our data. If we go further down, we can see the optimized versus raw motif pseudospectra. And here we can just only make it a little bit thicker so that we can see it a bit better. And then we can see the fragments that are representative of motif 137. If we go further down, we can see the different features in that motif. And these are here, so different fragments and losses and the probability that they will occur in the spectra where the motif was detected. So basically, if we go further down, here we can see which spectra is associated to these master motifs. And this is what we want to see or compare with the paper. So here it says that it was detected in erinaceriin N, and before looking into it, I have drawn the chemical structure or this molecule. So you see it here. And erinaceriin N is spectrum 547. So it's the document 547. So if we will just go here, and when we will look for that one, so we will look for spectra 547, we can look at it. We can see that the precursor MZ is 381 Daltons, which will make sense for our neutral mass of 380. So if we click it, then we can see in red highlighted those fragments that are associated to the master motif 137 and that are present in this spectrum. The same for the neutral losses as you see here. And what we would like to now check is how this can be corresponded to to the structures. So basically, let me just make this a little bit smaller. So we see that our molecule has two sides. And basically we have this part here and we have this part here. So if we will go back to the supposedly annotation from spec2vec, it seems to say that we have this aromatic ring with two nitrogens. However, if we would like to match this to our structure, we can start to play around. And what I did is that I started redrawing the structure and checking whether if I will fragment hypothetically the structure in different pieces. Basically, I can construct a fragment that will correspond to this mass. So 267 Daltons, and this is 168 Daltons in this point here. So we will just zoom in so that you see it. So this 168 Daltons is positively charged. So it means that the neutral mass of that fragment should be 167 and might be reflective of something like this. So as you see, the annotation based on spec2vec is not 100% accurate, but it can help us to see which kind of part or scaffold or subscaffold in the structure made sense. So this is actually very, very nice. And we can see that it is here. And if we will actually would like to check, so if we will calculate the neutral loss, we'll be doing this calculation. So it will be 380 Daltons minus 167, and it will be 213 Daltons, which correspond to that neutral mass. So that's very nice. And the same we could start doing for the other smaller fragments, which might be linked to further modifications of this substructure. All right, so if we will look now for the other master motif, which is a master motif 22, we can do a similar thing. So we will need to go back to the motif ranking, and here we will look for that one. So here we will click on it, and we will see that here the spec-to-bec annotation is suggesting these matches as you see here. So actually, it's important to know that this is, yeah, the suggested annotation is based on the spec-to-bec hit, but it could have a bigger, it could be a bigger molecule than actually the substructure that it is representing. So this is important to take into account. So here again, if we would like to see which are the corresponding fragments that are in our optimized pseudospectra, we can see this guy here at 70 Daltons and this guy here at 116 Daltons. So basically, it will again go down to our spectrum 547. We can see those fragments highlighted in the spectrum from erinacetine N. So here I try as well to do some similar analysis and try to match some of the substructures that are present in erinacetine N to the masses of the fragments that we see. So we see 116, so it means that the neutral mass of that fragment should be 115 Daltons, so it means that it remains, or a nitrogen remains on it, and something like this could be hypothetically possible. However, like we will need to really carefully look at it, and if possible, even incorporate like pseudo formula of those fragments to be really sure that is the actual hit. However, what we can see here is that we can actually associate those master motifs to structural insights of our molecule. So that's very cool, because if we would like to look at the diversity of these master motifs and in overall or ultimately of the erinacerines of this subclass, then we can just use the master motifs as proxies to look for other derivatives, which is what is done here on the paper. So if you're interested in that, then you can have a further look at the case study in the paper and then see how you can use the information or the insights that we just described to look for novel derivatives. So I would like to use a second example, which is now described in the supplementary material of the preprint, to look at a different class of molecules. So while it loads, we will just go back to the motif rankings. And here in the supplementary material, we will download this PDF. So I will just go to it. And now the case study that I want to bring attention to is these herisenons. And specifically, we will look for herisenons F and G, which have master motif 90, master motif 186, and master motif 163. So what we see is that also these molecules have different subparts and they share this bicyclic core. So we want to see if the master motifs capture this. So let us go back to our data. And in the motif rankings, we will look for master motif 90. So we will look at it. So if in this case, you see that these are two of the supposed annotations from the spec to bec, maybe we will need to make sense of what it means. So basically, we see that the optimized fragments or the optimized pseudospectrum contains only one fragment here, or one main fragment at 83 Daltons. And then we can also look for the respective spectra. So I also have done this here. So if we will go up and look for this one, which is 250601. So this will represent actually this molecule heresy on F, then we could basically try to match the fragments to the structure. So 2501. So then let us look for this one. And this is what we see here. So basically it's the same that we see here in the supplementary material of the paper. So basically, in this case, what we would like to match is maybe first this fragment at 83 Daltons, and it will actually make sense to look at the structure first. So if we see in our structure, we have this fatty acid, which is esterified to the molecule. Then we have the bicyclic core, and then we have these aliphatic side chains on the right side. So since we have a very small fragment, so 83 Daltons might represent actually something that happens in this part here. And this will also make sense with this small annotation, this match number 2. So this somehow resembles this part of the structure. So we want to see whether if we can match something like this. So if you see, these small 2 fragments might be equal representations of this part of the herizenons. However, this will needs to be double checked, and this can be further it's further discussed in the supplementary material. So if you're interested, let us look now for the second master motif. So for example, master motif 186 Daltons. So this is master motif 186. So let us look for that one. And here we see it. So this is already very important to see, because if we will open side by side our annotations from the spec to spec versus the structures of the molecule, what we can see is that both suggestions point to a bicyclic system, which basically we see here. So it's mainly this part here, which actually is very nice to see, because then master motif 186 is representative of this substructure, so this, which is the core scaffold or the backbone of this compound class. Now let us see if we can match the fragments that are associated to this master motif. So if we go down, then we here click again in the spectrum of interest, and we see some fragments of interest already here. So if we will just start by the biggest fragment, which is at 315 Daltons, we can actually see that we will mainly get, or we could get something that represents this right part of the structure. That's very cool, because if we will start then going down and seeing whether we can match some of the further fragments, we can look at this one. It's 177 Daltons, so meaning that the neutral mass is 176, and we see that that might actually represent something like this. So that's very interesting to see. And what we see further here in this case is that maybe these neutral losses are associated to the loss of this main part of the molecule, which is including this bicyclic core. So this actually is very helpful for us to make sense and put together the master motifs as a structural guidance of maybe further derivatives. So that's very interesting to see. And this is further then discussed in the preprint as well. So, okay, so right now we have seen how these 2 examples deal with different master motifs and come together to explain different substructure of these 2 secondary metabolite families. And basically, we can now go to the different tabs that are still waiting for us. So the first one is the spectra search. And basically, let's say that we are interested in compounds around 310 Daltons, and let's say 450, because we assume, let's say, that the arena serines are between this range of molecular weights, and we would like to look for all of the arena serines with this fragment. So 168 Daltons that we already saw, that is it includes the left side of the molecule with this aromatic ring, which contains a nitrogen. And what we can see here is that 52 spectra are between this mass range, and they contain this fragment at 168.07. So this is very interesting, because then based on this, we can do specific queries and try to see which mass to motif they contain. Now, if we'll go to the View Network tab, here we get a different kind of visualization. And what we can see here is that we will see a network visualization that shows the motifs and their corresponding fragment losses in a very interactive way. So here, what we will see is that we will see motifs in blue, fragments in green, and neutral losses in yellow. So like this, we can actually start looking and seeing whether we find mass to motifs that they share different fragments or losses. So that's interesting to see how this mass to motif diversified, and even if some of them are congruent or coherent according, so they might even represent the same substructure. So if we click on those, we can see, for example, motif 2 is associated to this molecule here, and the main fragment is this, 109 Daltons, and we can try to look for those that we are interested in. So then this is actually quite nice to interactively see how this comes together and how different fragments are represented by similar or different motifs. So yeah, then this can be used as further inputs to look at like the different things that our master motifs represent. The last step is the motif search. So basically here, if we would remember, in the motif ranking, we have a list of the master motifs that are identified by our analysis. And basically, if you see here, the matching hits is empty. However, in this motif search, it will enable to match these master motifs to some of the libraries that are included in MotifDB. MotifDB is, as we explained before, the repository of manually curated master motifs. So let's say right now we will use the GMPS library, master motifs, or in this case, we will also use, let's say, the MassBank library. It will compute the spec-to-spec similarities between the pseudospectra and those master motifs. Then it will take us a moment. So it's updating, and now what we can see is that we have this number of matches, and basically we can go through them. So again, if we go back to our motif ranking tab, now we can see here the different hits. So let's say we will look again for some of them. So let's say 22, and we can see here now the annotations. So if we go again here, it will be here enabled that our master motifs has these hits here in GMPS or MassBank, and so on, so on. So that's very interesting to see. And yeah, basically with this, we have already gone through the visualization website for MS2LDA 2.0. I hope that this is useful for all of you. And yeah, with this, then we will continue in our next video on actually knowing how to process our data with MS2LDA 2.0. So stay tuned. Bye.